Okay, thank you so much for the prayer. My name is Teacher Mugumia Oswald, and once again I'll be taking you through chemistry. In the first phase we looked at chlorine and its compounds, and we had a test at the end, and I'd shared with you the notes of that topic. So today I want us to start on something new, and we call it applied chemistry. It is also just a branch of chemistry, whereby we want to learn how we can apply a knowledge of chemistry, or what chemistry can do in our society. So get ready, and we start. So that is our topic, or our chapter, applied chemistry, and we shall focus on metals and metal extraction in this case. So we shall first focus on metals and metal extractions. So once again, this is not something new. We shall look at familiar things, the ones we've seen before, only that we are going to give much emphasis. We are going to also give more details. So all of us, we know metals. Since we have the knowledge about metals, and then now we want to know how can we extract them, how can we get them wherever they are found. So metals, we can say that metals are electropositive, and when we say electropositive, we mean that they can ionize by losing electrons, or we can say by loss of electrons to form positively charged ions. For anything to be electropositive, it must lose an electron. It can be one electron, they can be two, they can be three. So that's what we mean by being electropositive. So we are saying metals are electropositive, or that is to say they ionize by loss of electrons to form positively charged ions. Just like how we looked at this in atomic structure, and when we're looking at formation of ions. Take an example. If I have a metal of sodium, if I have my sodium metal here, sodium being a metal, it has loose electrons to form an ion, or to form a sodium ion. So it is going to form sodium ion, which is like this. And by having a positive charge, it means that it has lost one electron. And to balance the equation, we just add an electron. If it was maybe calcium would lose 2 electrons. That's why we have 2 plus. And the way we write this, it's supposed to be the plus behind that 2. If you write, for example, if you write calcium ion like this, with a plus in front, then that would be wrong. So it has to be behind. So all metals do that. As long as it is a metal, it will have to lose electrons to form ions. So we shall look at different metals, and we see how they can be extracted, or how they can be got wherever they are found. So we also call them reducing agents. What do we mean by reducing agents? It means that in the process of losing the electrons, those electrons which are lost are gained by nonmetals. Remember, we can define reduction as the gaining of electrons. So that element or that metal that causes the gaining of electrons, we call it a reducing agent. So these metals, since they lose electrons, take an example. If sodium is reacting with the chlorine, we shall form what we call sodium chloride. We shall form sodium chloride. If you have to balance it, I think here we put a 2 and a 2 here. So we are having this reaction whereby sodium is a metal and chlorine is a non-metal. So what do we do? It means that to have this reaction or to have this sodium chloride, it was a sodium ion. It was a sodium ion reacting with a chloride ion. In other words, this sodium lost one electron, which was later gained by chlorine, and that's why chlorine has a minus charge. Whenever an element gains an electron, it gets a minus charge. So sodium donated or lost one electron that was gained by chlorine. So we call sodium a reducing agent by donating that electron that was gained by chlorine. Yes, Benjamin.
So are you hearing me?
You're breaking, not clear.
I wanted to ask about the way you've balanced this equation. I'm not understanding. I never understood the way you balanced it. I just heard you saying the 2 here and the 2 here. I did not understand where the 2 came from.
Okay. Thank you.
Yes.
So Benjamin is asking how I balance this equation. Here we are having, if I'm to do it again, unless if I made a mistake, if I'm to rub this, but I'll be very fast since we are not in that topic of balancing equations. I will just be fast. So we are having, I just gave an example. We are having sodium. We are having sodium, which is a solid. Then we are having chlorine, which is a gas. And remember, chlorine is diatomic. So there are 2 atoms. So here we shall get sodium chloride. We shall get sodium chloride, and this is a solid. So why did I have to put a 2 here and a 2 here? Here we are having 2 atoms of chlorine. Here this side we are having only 1. So we need to balance the chlorine atoms. So that's why I put a 2 here. And when I put a 2 there, it affected the number of sodium atoms on the right hand side. So remember, this is the right hand side. This is the right hand side. Then this is the left hand side. Reactants on the left, then products on the right. So these 2 affected the sodium. So now there are 2. So that's why I had to come here and put a 2. So that is how I came up with such reaction, such equation. I hope Benjamin it is clear now. You can raise up the hand if it is clear. Benjamin. Okay, Regan, I hope you're not asking about balancing equations because this is a different topic. Regan?
Master, I'm not asking about balancing equations.
Okay.
My question is about the last statement that they are therefore reducing agents. I was requesting for more explanation about that last sentence.
Okay, thank you. So, you can mute yourself, Benjamin, rather Regan. Okay. So what I meant was that these metals are able to donate. Donate is like giving away. They are able to give away their electrons, of which those electrons are gained by a non-metal. So in chemistry, whenever an element is able to give away an electron, which is later gained by a non-metal, and then we call it a reducing agent. I'm trying to use a simple language. So what we should know is that metals are reducing agents. It's because of that property that they can lose electrons. So that's what we should go with. So from there, let's look at the occurrence of metals. When we talk of occurrence, we want to find out where they are found. How can we get them if we need them? Where can we find them if we need them? That's what we are going now to concentrate on. So metals occur in what we call in the earth crust, which is summarized as ores. So in the earth crust we have there some things which are called ores, and we can define an ore as a rock which contains metal compounds from which metals can be extracted. I'm not saying that this is the only definition. We have different definitions, but I think to me this is the simplest. That is to me, but you find other definitions. So an ore is a rock which contains metal compounds from which metals can be extracted. So in the earth crust we have different ores there. We have such rocks which contain different metals. For example, we have rock salt. We have rock salt. Which is the same as chloride, and that ore we can use it to extract or to get sodium. So here, the name of the ore is rock salt. Then the chemical name of the ore, we call it sodium chloride. So here it should be, we call it sodium chloride. That is the chemical name of the ore. Then the chemical formula is this one. So there are different things they can ask you about this. They can ask you the name of the ore from which sodium can be extracted. Then from there they can ask you the name of that ore, the chemical name of that ore which is sodium chloride, then the formula, the chemical formula of the ore. So those are 3 questions. Then we also have another ore. Here we are just sampling. We have what we call a spathic iron ore, which we can call iron 2 carbonate. So once again, the name of the ore is spathic iron ore. Then this is the chemical. Let me use a different color. So this is the chemical formula of the ore. Then the name would be iron 2 carbonate. Iron 2 carbonate. That would be the chemical name of the ore. I hope I'm clear there. Then we go to another example of the ore. Let me now use maybe I can use black. So we have another example, which is iron pyrite. Iron pyrite, or what we call, this is iron sulfide, and it is for iron. So once again, it's the name, this is the chemical formula, and also then the name of the chemical name would be iron 2 sulfide, that is for iron. So members, here we are just summarizing, or we are just giving a few examples of ores. We have more than this. And for an ore, if it is to be used to extract a metal, it must be containing that particular metal. Like here, if we want sodium, we shall use an ore which contains sodium. If you want iron, we shall use an ore which contains iron. The same applies here. So that ore must be containing the metal you are extracting, and that metal must be in a bigger percentage. Later on, we shall find that some ores contain impurities which can be removed during the extraction. So whenever we are extracting such metals, there are some impurities that we need to remove. What we call purification of the ore, or concentration of the ore, as we shall see. Any questions on that? Any questions on that? If you have a question concerning what we have so far looked at, the one we have on our screen. There is someone without the name. Unmute and tell us your name. What is your name?
Yes, I have a.
Unmute. I'm unmuting, then for you, unmuting yourself. Mute.
I'm asking that are there also other minerals extracted from iron ores?
Yeah, we have other minerals. But at times our interest is in a particular metal. If it is iron, we concentrate on removing the iron. But there are other smaller minerals in that ore. But remember, as I said, the metal you are extracting must be at least in a bigger percentage. So that
Okay.
it can purify it, get it from there. And I'm also requesting that you can rename yourself. This is the name of an android, so I don't know whether you're a robot. You can rename yourself. Thank you. Then Marvin.
Excuse me, teacher.
Yes, please.
I didn't understand because you were off.
I was off or you were off?
We were off.
So you have just joined, eh? Marvin, it was because of network. We shall discuss later. Your network is
Yes.
not even clear. Then Regan.
Now, Master, I was asking
Mm.
that when we are extracting, like for instance, sodium chloride,
Mm.
so that the sodium has to be more than the chloride, the sodium atoms.
Okay, thank you. So Regan, what we are saying here is that this is the ore. This is the whole thing, the one we call the ore. But within our ore, we are interested in only sodium. So what we do, we shall need to do our best to make sure that we remove chlorine from there and we remain with only sodium. And like I said, an ore, it is supposed to be, or under normal conditions, it must be containing a bigger percentage of the metal you are extracting. But if it is not so, it can still be extracted. That is, if it is in a small percentage, it can still be extracted. But the other methods change, but it can still be extracted. So we are extracting metals, not the chlorine atoms. I hope I'm clear there. So now we can continue. So let's look at now the extraction of metals. And we say that for a metal to be extracted, its concentration in a given ore must be high, like I said. That ore must be containing a higher percentage of the metal you are extracting. If it is sodium chloride, then the sodium must be in a higher percentage than the chlorine. In other words, we can say maybe 70%. So if we say 70%, it means that chlorine is either in 30%, or chlorine and other impurities are within that 30%. So that's what we mean by saying that its concentration in a given ore must be high. Therefore, it is necessary to concentrate, or what we can call purify, the ore before extracting the metal. So what do we mean by concentrating the ore or purifying? That means that we need to remove other impurities which might be present. So we try, or we undergo certain processes to make sure that the impurities are removed, so that we can remain with a pure metal that we are interested in. So that takes us to the methods of extraction. So we have different methods which are used to extract different metals. So one of the properties that contribute the method to be used, it must be position of the metal in the electrochemical, or what we call reactivity series. So we need to be having methods, the highly reactive metals. We also have methods that we use to extract the middle metals, and also the methods we use to extract the less reactive metals. So here we have a sample, or we have our reactivity series. So this is a reactive series, or what we call electrochemical series. So the ones we have in the brackets. So for the case of potassium, sodium, calcium, magnesium, and aluminium, the ones I'm going to circle. So the ones which are in this red circle are ones so we have potassium, we have lithium, magnesium, aluminium. So these are very reactive metals, and therefore they form very stable compounds. So we shall need a method that can be used to extract or to make sure that we get, let's say, calcium from those stable compounds. And again, they are not found as free elements. What do we mean by saying free elements? Take an example. If you look at atmosphere, like the way we define atmosphere, that is a mixture of gases. So we can find some elements in the atmosphere as free elements. They are not in any compound. If you want, for example, nitrogen, you can find nitrogen gas in the atmosphere. If you want oxygen, you can also find it in the atmosphere, like that, as free elements or molecules. But for these metals, they don't exist as free elements. Yes, Marvin?
I wanted to ask, which specific methods do we use to purify the metals?
Okay, we are coming to that. Just to be patient a bit. We are coming. We are almost close.
Okay. Yeah.
Okay, thank you. Then we have a robot here. Tekno W2. Tekno W2. If you don't rename your device, I'm likely to call you a robot. So you first tell us your name if you are not a robot.
I'm Pius, teacher.
Okay, please, Cyrus.
Teacher, what I'm asking is about what do you mean by the meaning of a stable compound? Does it mean that it doesn't lose an electron to become stable?
It means that the compounds which are formed by such elements, they have enough strength. Like if you are decompose them, you need much energy. That's what we mean by being stable. So they are stable to any condition.
Okay, teacher.
If it is heating, they require too much heat. Unlike if it is unstable. Okay, thank you. Okay. We can consider, for example, if you are heating a stone and maybe a candle. A candle, you just need some heat. It will start melting. But if it is a stone, you need a lot of heat. So the stone is stable, then the candle is not stable if you compare the two. But I request that you put your name Cyrus on your device. Then Eve, are you the Eve in the Bible or Eve? Unmute yourself. Eve. Meaning if you can't unmute yourself, then okay. So we continue.
Excuse me, teacher. You're breaking. You're on and off. We can't hear you clearly.
Okay, sorry about that. But I have a feeling that maybe you are not the one hearing me. You try to check your network as I also try to check mine.
Okay.
right. Someone is saying that my network is clear. Yeah, it was, I think it is her network, but she's going to check it out. Let's continue. So the elements, other metals which are very active and they form stable compounds, we can extract them from those stable compounds by using a method that we call electrolysis. We call it electrolysis. I don't know how many of you have so far looked at electrolysis, but that is when we have a compound that gets decomposed whenever current is passed through it. So the compound decomposes. For example, I'm just trying to summarize that. For example, if you look at the car batteries, some of them contain sulfuric acid. So this is our compound, sulfuric acid. And when current is generated and is passed through sulfuric acid in the car battery, this will decompose to give us hydrogen ions and also sulfate ions. So that is what happens. So this is this is what we call an electrolyte. Then these are ions which are formed when current is passed through the sulfuric acid. I will not go into the details of electrolysis, but that's the method we use for extraction of those very reactive metals from their stable compounds. A number might come in paper 1 asking which of the following metals is extracted by electrolysis. So they can put for you one of these 5 elements. If it is sodium, to be correct, potassium, correct, calcium, correct, magnesium, correct, and aluminium. Still in paper 1, there are those numbers where we're given more than one answer. They can ask you which of the following metals are extracted using electrolysis. They can put for you either 2 metals, or they can put 3, or we can put only 1. Depending on the question choice as yes, this is Nashira. Nashira, please unmute. Unmute and talk to us.
I was asking it. Hello?
Hello, I'm hearing.
So can electrolysis be called reduction also?
No, those are 2 different things.
Okay.
Electrolysis, it is a complete topic, so I can't just summarize it in one lesson. But if time allows, we shall look at it. But it's a complete topic. Okay, thank you. You can mute yourself. All right. Then we go on. Metals like zinc, iron, lead and copper. Lead and copper. Let me first check on these people. Yes, Timothy. Timothy, unmute. Members, if you're given a chance to talk, please be fast so that we can save time. Yes, Timothy.
Yeah, I was saying that are the metals, when they are reducing them into atoms, are they reduced according to their reactivity series?
Yes, please. Okay. So we are saying that zinc, iron, lead, and copper. For them, their ores. Their ores are oxides, some are sulfides, and some are carbonates. So these are the ones which are common. But we have other ores where we can get either copper or zinc or iron. Like the way we looked at from above, we found that the ore for iron, the one we had above, it was iron 2 carbonate, which was a carbonate. So in this case, these metals are extracted by reduction, a reduction of the ores. For example, if I had a zinc oxide, if my ore was zinc oxide and I'm reducing it, it means that I would apply a reducing agent, which is either carbon or carbon monoxide. Why do we use carbon or carbon monoxide? Is because they are cheap and they are readily available. So I'll get zinc oxide, which is in this case my ore, which contains zinc. Then I add a reducing agent. I can add one of the two, assuming that I've added carbon monoxide, which is a gas. So my zinc oxide will be reduced to zinc, the one I want, the zinc metal. Then the carbon monoxide will be oxidized to carbon dioxide gas. Carbon dioxide gas. My equation is balanced. Here we have zinc 1, zinc 1. Oxygen we have 2, 1 plus 1, 2. Here we have 2 carbon, we have 1, 1. So the equation is balanced. Blessing is asking that she thought that hydrogen was also among the reactivity series. Yes, it is among them, but this time we are concentrating on metals only. We are only concentrating on metals because we are looking at extraction of metals. So hydrogen is supposed to be here. It is supposed to be between lead and copper. So we are just ignoring it, given that it is not a metal. Okay, I hope that one is clear. Then from there, let's look at the last metals, the ones which are not very reactive. So here we have mercury, we have silver, and also have gold. So once again, these ones are not very reactive, and therefore they are found as free elements. So for these ones, you can find mercury as a free element, not in any compound. Not in any compound. Also, silver can be found as a free element, not in any compound. So they are the extract, since they form compounds. They can be extracted by mere heating of the ore. So these ones can easily be extracted. So these are different methods used of these metals. The ones we have listed here. The ones in red, very reactive, we use electrolysis. The ones in blue, they are moderately reactive, and we use oxides, sulfides, carbonates, and so on. Then the ones in red, they are not very reactive, and they can exist as free elements. Then someone is similar that metals are they reduced to their reactivity series? Yes, their reactivity series. For example, if I have let's say if I have a zinc oxide I'm responding to Timothy. If I have zinc oxide reacting with magnesium, which is also a solid. If you are to check in the reactivity series, magnesium is higher in a series than zinc. So magnesium can reduce zinc, whereby we shall form now, it will be magnesium oxide, and this time it will be zinc metal. So this is the reduction. So magnesium has reduced zinc oxide to zinc, then for it has been oxidized to magnesium oxide. The reaction is impossible. If at all I had let's say calcium oxide reacting with let's say lead, so this reaction cannot take place. This reaction cannot take place because lead can't reduce calcium oxide. Lead cannot reduce calcium oxide. Reason, lead is lower than calcium in the series. I hope Timothy it is clear. Daphne?
Yes, sir. Sir, I was asking that do these last elements, like, do they react with cold water or steam or not?
Okay, thank you. They can react, but there we shall need apply some external conditions. We can apply, like for example, a catalyst. We can apply temperature, we can apply pressure for them to react. But under normal conditions, they might not react. Okay, so that's all with the methods. So let's look at sodium. We are picking sodium right now. Here we are going to show the principal ores, or the chief ores, or the common ores from where we can extract sodium, or where we can get sodium. One, like we saw before, we have a rock salt, and I say this is the name of the ore, then this is the chemical name, and now this is the chemical formula of the ore. The name, chemical name, chemical formula of the ore, and this is common in salt lakes like Katwe in Uganda. Then we also have soda ash, which is sodium carbonate. So once again, this is the name, chemical formula, and this is common in like Magadi, that is in Kenya. Timothy?
Isn't sodium chloride the same as salt?
Yes, the common salt. But of course, the common salt we have, it is after being purified. That's why it looks white.
Okay.
Okay. Looking at the rock salt in the lake, by the same as salt we use at home. Then also have sodium nitrate. The one we can call the chemical name, it is chili saltpetre. Then the chemical formula is this one, which is the same as sodium nitrate, and is found in Chile. Those who support Arsenal, that is where Sanchez come from. So we continue. We look at extraction of sodium. Extraction of sodium. So we want to go into the process of extracting sodium. The steps we follow, the apparatus we use, or if there is a machine that we use. So this is the time. So sodium is extracted by electrolysis. Remember, it is among the very reactive metals, and that's why we are saying that it is extracted by electrolysis. From which ore? From the ore we call sodium chloride. This is the method of extraction, and this is the ore, sodium chloride, in the Downs shell. In the Downs cell, using Downs process. This is someone's name that invented that process. Downs cell using Downs process. Yes, Eve. If your hand was up, maybe it was by mistake. You people, when you raise up your hand, make sure it stays there until when I select you. So Mahinda had put up his hand but disappeared. Okay, let's continue. So we are saying that this is the process, this is the method of extraction, this is the ore, and this is now the apparatus or the equipment that we use to extract, and we call it Downs cell, and we call the process Downs process. So we extract sodium using Downs process. Then we continue. As the melting point of sodium chloride is high, as the melting point of sodium chloride is high, and it is about 800 degrees Celsius, and then we add calcium chloride, which is to lower the melting point of sodium chloride, or the melting point of the ore. And that's why I put the word lower in bold so that it can be very clear. So they can ask, what is the use of calcium chloride in the extraction of sodium when using sodium chloride as the ore? It is to lower the melting point of the ore. And again, if you're not very sure of the temperature, let's say if you're not sure of the temperature is 800, please don't mention it anywhere. Just say calcium chloride is used to lower the melting point, full stop. Don't start fidgeting around saying 800, then the other side you say 500. That would be wrong. Someone is saying that my network is not clear. Yes, it happens, but it will be clear. Let's be patient with each other as we also cross-check with the network. Okay, it seems Ronnie, your network is the one which is not clear, because members here are saying that mine is very clear. Okay, so the melting point of the sodium chloride is lowered by adding calcium chloride. So this is a Downs cell. This is the Downs cell. The whole of this, it is the Downs cell. This is just a diagram of the Downs cell. But you know, technology simplified everything. I'm going to share a video. This cell, we shall in detail. We shall see what takes place. We shall see how sodium chloride is added with calcium chloride. We shall see how chlorine comes out and all that. So let's pay attention. I'm going to share a short video. I'm going to share a short video. Let me first stop sharing, then I share again. I'm going to share a video. Okay, so I hope you can see the video is on YouTube, so we can get anything from the YouTube, but after looking at many videos I found that this is the best so far, but you can look for another one even better in understanding. I want to share it with the sound. Okay, all right, so I'm going to make sure you pay attention and you take notes.
Sodium metal is commercially prepared by Downs process. This cell is bought with fire bricks.
Let's start it again.
Graphite anode is placed at the center of the tank, and ring-shaped iron cathode. Sodium metal is commercially prepared by Downs process. This cell is made up of iron box, lined with fire bricks. Graphite anode is placed at the center of the tank, and ring-shaped iron cathode is placed outside the anode. Cathode and anode is separate screen. This screen separates sodium and chlorine ions. A mixture of sodium chloride and calcium chloride is poured in the cylinder. Calcium chloride is added to decrease the temperature of NaCl. When electricity is passed through the cell, NaCl breaks down into its components. Sodium ions are collected at cathode, and chlorine ions moves towards the anode. The reaction at cathode is sodium ions reduce at cathode and forms sodium metal. The reaction at anode is chlorine ions are oxidized to give chlorine gas. Liquid sodium rises up and is stored in a container. 99.9% pure sodium metal is collected in the container. The chlorine gas is collected from the top of the cell.
Let's play it again for the last time.
Sodium metal is commercially prepared by Downs process. The cell is made up of iron box, lined with fire bricks.
Members, what we are looking at here, for example, this one, if you take a picture, you will see that it looks like the same, like the one we have. So this picture here represents what we have the other side on paper.
Graphite anode is placed at the center of the tank, and ring-shaped iron cathode is placed outside the anode. The cathode and anode is separated by iron screen. This screen separates sodium and chlorine ions. A mixture of sodium chloride and calcium chloride is poured in the cylinder. Calcium chloride is added to decrease the temperature of NaCl. When electricity is passed through the cell, NaCl breaks down into its components. Sodium ions are collected at cathode, and chlorine ions moves towards the anode. The reaction at cathode is sodium ions reduce at cathode and forms sodium metal. The reaction at anode is chlorine ions are oxidized to give chlorine gas. Liquid sodium rises up and is stored in a container. 99.9% pure sodium metal is collected in the container. The chlorine gas is collected from the top of the cell.
That is
We all know the crazy chaos caused by trying to use more than one app for productivity.
so what we have so far looked at, or what we have watched, it is this diagram. So the other one was in it was in a video form. So this is the picture, the cross section of the other one. So what we shall do, when we meet next time, we shall have the explanation of the Downs process. That will be in our next lesson. So we shall see part by part, and we get more explanation, but it doesn't stop you from making more research and understanding more. So I'm going to welcome like 2 questions, then we call it a day, because we are past time. We are 3 minutes late, 3 minutes past time. 2 questions if they are there. If they are not, okay. Yes, Timothy.
Is the Downs process also used to extract other metals apart from sodium?
It is best for sodium. It can be used for other metals, but it's best for sodium.
Okay.
All right, thank you. Last question. Last question. Someone is asking that according to the video, it showed a graphite anode, but the diagram shows carbon anode. I don't know whether you have already covered the topic of carbon and its compounds, but graphite is an allotrope of carbon. In other words, graphite is made of carbon. They are the same. Graphite is made of carbon. And if you had read the equation of graphite, you use the symbol for carbon. So they are the same. Someone saying thank you. Yeah, you're welcome. So I think those are 2 questions. Can we have a volunteer to give us a closing prayer? The other time I think we had a lady. Let's have a gentleman. Isaac, even your name is in the Bible. Isaac, can lead us in prayer. Isaac, Jacob, and Abraham.
Okay. May we humble ourselves for a prayer? Lord Father, we thank you for today. We thank you for the lesson that you have offered to us, Lord. We thank you. We thank you, Father, that for the teacher who has been with us. from the first minute up to the last minute, Lord Father. And we ask you to bless us, to bless our minds so that we are able to understand, and also bless our memory so that we are able to capture and remember everything. In Jesus' mighty name we pray.
Amen.
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 Teacher. Bye.
Thank you, teacher, for that lesson.